My name is Eric Nichols, and today I would like to talk about dynamic programming and machine learning, using an example from natural language processing. First, I will give a dynamic programming refresher. Dynamic programming is a design technique that is characterized by several hallmarks. First and foremost, it is designed to improve efficiency by defining a problem as the recursive solution of several subproblems, thus allowing the elimination of redundant calculations. These subproblems have several characteristics. The first is that a recursive solution to the main problem contains many repeating subproblems, some of which can be eliminated. The second is that these subproblems exhibit what is known as optimal substructure. This means that the solutions of the subproblems can be combined to get the optimal solution of a larger problem. Today I'm going to introduce dynamic programming using a classic computer science example, the shortest path search. I have chosen the shortest path search because it allows access to a large number of dynamic programming algorithms that can display several interesting features. First, some definitions. We are given a directed graph with vertices and edges, v and e, and an edge weight function mapping e to real numbers where w of e is greater than or equal to 0. Our goal is to find the shortest path between two nodes, with a path weight defined by the weight function w of p, which is the sum of all of the edge weights of the edges in the path. We also have a shortest path function defined as delta u and v, which is the minimal wp, where all of the paths are from u to v. So we are going to solve this problem using the Dijkstra's algorithm. Dijkstra's algorithm is a classic example of dynamic programming, and as such it exhibits dynamic programming characteristics as follows. Dijkstra's algorithm takes the approach of recording the shortest path cost from the start vertex at each vertex. This allows it to eliminate redundant computations, thus addressing the overlapping subproblems problem. Next, Dijkstra's algorithm operates by expanding vertices by ascending cost. This makes it fundamentally a greedy search algorithm. Finally, Dijkstra's algorithm works by updating the shortest path cost to neighbors by adding the cost to the current node to the neighbor's path. This demonstrates optimal substructure because shortest paths are composed by definition of shortest subpaths. Dijkstra's algorithm is composed of three main sections. It has an initialization section where the start node is given the lowest possible value in the graph of 0, and each vertex that is not the start node is given the value of infinity. It should be noted that Dijkstra's algorithm does not handle edges with negative weights. There are other alternatives that do. Next, we create an empty set to store vertexes in after they have been processed and create an empty priority queue. We then load the empty priority queue with all of the vertexes in V. Next, we enter the main loop of the algorithm that will alternate between an extraction and a relaxation phase. While there are nodes remaining in the priority queue, we carry out the following actions. We extract from the priority queue the vertex with the current shortest path, and we add that vertex to the already processed set S. That is the extraction process. Next, we move on to the relaxation process, where for each of the current vertex's neighbors V, we check to see if the current cost to get to V is greater than the shortest path distance to U plus the distance from U to V. If the current shortest path for dV is greater than that, then we know we found a new shortest path, and we update the values in the priority queue accordingly. Now I'll give a concrete example. We have our graph from before, and first we're going to enter into the initialization process. We give A, the start node, the value 0, and all the other nodes the value is infinity. We're going to extract A from the priority queue and add it to our already processed set S. Next, we're going to relax the edges of A and see if we cannot find shorter paths for the nodes that are connected to A. Because nodes B and C currently have the value of infinity, we find that the edge values are indeed less, so we assign B and C 10 and 3 respectively. Because these values get updated in the priority queue, when the priority queue moves to the next vertex, it's going to select C because C has the shortest current path in the priority queue. So we next extract C, add it to the processed nodes set, and proceed to relax its edges, looking for better paths. As we find better paths, we add them to the priority queue and continue processing. Moving on to node E, relaxing its edges, moving to B, relaxing its edges, and finally moving to D. Once we have finished with D, the processing completes, and in the priority queue, we have, as highlighted in red, the distance from the start node, the shortest path distance from the start node to each of the other nodes in the graph.